Hey guys, welcome to DDM 4422 Pro Tools 101. First off, I hope all of you are in good health and are ready to begin. The reason we were unable to commence before was due to the fact that this course needs a textbook, and thanks to Avid, you should all have one by now. Last week, I shared a video with y'all on how to download and install Pro Tools onto your own personal computers. I hope y'all have all taken the time to do it and have successfully installed Pro Tools. The video had been made available to you to view on YouTube, through Teams and through Moodle. I had also shared a walkthrough on how to download and use your ebook through the same channels. I'm guessing y'all have managed to do that as well, as I did not receive any complaints so far. So, Pro Tools. Now, before we dive in, I'd like to just highlight the fact that we shall be discussing many hotkeys in this module. Many of the keyboard commands in Pro Tools use modifier keys, which are keys pressed in combination with other keys or with perhaps a mouse action. These modifier keys are different on Macs and in Windows. And since I know not all of you are on Macs, I just wanted to make you all aware of these modifiers and their Windows equivalents. Like the equivalent of the command key in the Mac is the control key in Windows. So if you're doing a simple thing like copy and paste, on a Mac you'd use Command C to copy and Command V to paste. But in Windows, you would use Control C to copy and Control V to paste. On the Mac, we also have an Option key on our keyboards. The equivalent of this in Windows is the Alt key. So while I teach, if I say we have to Option click on something, on Windows, you will do Alt click instead. Similarly, the Control key on the Mac correlates to the Start key in Windows. The Return key on the Mac is the same as the Enter key in Windows. And the Delete key on a Mac is the Backspace key on your Windows keyboards. A thing about the Enter key though. If you're using a full-size keyboard, that is the one with the number pad, please remember that the Return key on the Mac does not mean the Enter key that is on the number pad. In fact, none of the keys on the number pad are even the same as the keys on the QWERTY keyboard. And this too is important, because if I ask you to press Command 1, pressing the 1 on the number keypad is not the same as pressing the 1 on the number row on the QWERTY side of your keyboard. It is two completely different instructions. But don't worry, I'll tell you when you need to press which one. So please pay close attention to such modifiers and just be aware of the keys you need to press for which task. The book actually tells you both the Mac and Windows equivalent of all these hotkeys whenever we need to use them. Another thing I'd like to mention, since many of you are new to the world of the Mac, on a Mac, when you click on the little red bubble on the top left corner of the window, you are not quitting the application. You are only closing the window that you are seeing. In Windows, if you click on the red X, you are actually quitting the application itself. But on a Mac, the app still runs in the background. As media students, you should be aware that having an app run in the background does take up quite a bit of your system's resources. So if you are a Mac user, always remember to click on the name of the app up in the menu and select Quit to completely exit from the app. Our module spans over 10 chapters, and as I mentioned in my introductory video, these 10 chapters are directly from the textbook. So technically, this curriculum is designed by Avid and is delivered in the exact same way all over the world. In the first two chapters, we will go over some of the basic fundamentals of audio and have a brief overview of Pro Tools itself. We shall use this time to familiarize ourselves with the platform, its capabilities, and most importantly, its interface. In chapters 3 through 6, we shall learn about the creation of media and how we can import external media into our sessions. We shall also learn some of the basic concepts of organizing the elements of our session, like naming our tracks, or perhaps color coding them based on their types, etc. In chapters 7 and 8, we shall focus on navigating ourselves within Pro Tools. For example, the various scroll options, or how to quickly locate which part of our timeline is playing at that moment. We shall also go over some of the basic editing techniques that Pro Tools has to offer. And lastly, in chapters 9 and 10, we shall go over some of the basic mixing techniques, get an understanding of how Pro Tools handles the flow of audio through it, the signal flow. We shall also learn about ways in which we can finish up our session by exporting or bouncing our final mixes, and if needed, how to burn some CDs as well. Your continuous assessments, or CAs, for this module account for 60% of your final grade. They are directly linked to the 10 chapters in the textbook too. Every chapter will have one assignment for you to do as homework. Don't be worried, it may sound like a lot, but they are all via Moodle, which means they are all mostly multiple choice or true and false type of questions. For every assignment, you will have a 7-day deadline, which means you will need to finish it before our next class. If you fail to submit it on time, you can still do it, but you will get only a pass or a fail grade for that CA. Which means if you are late and you get 80 out of 100 in that assignment, it will be marked down to just a 40. So please try and be on time. All of your assignments are open book, which means you can refer to the textbook as you're doing it at home. And you have only one attempt with it every time. That doesn't mean you have to finish it in one sitting. You can start the quiz today, you can do 2 questions, then take a break, come back tomorrow and continue, no problem. But once you answer a question, you can't change your answer. You can't redo the assignment. I'd like to stress on 2 points at this time. Open book does not mean you look for the answers in the textbook after reading the question. Open book means you study from the book first and then attempt the quiz in Moodle. Of course, if you are confused, you can always refer to the book to resolve your confusion. But if you comb through the textbook for every single question's answer, you are not going to learn anything that way. So trust yourself. Try and understand the question properly and then think back to what we have discussed and what you have read in the book. That is the right way to study. Since your CA accounts for 60% of your final grade, this module is a very high scoring module. Technically, if you do all your CAs on time and do them well, you can actually score the full 60% from it, which can boost your overall GPA in the program. So please do not underestimate this module. Lastly, when you are doing your CA and you come across a doubt, or perhaps you haven't understood something properly, feel free to reach out to me directly via Teams. I will be more than happy to schedule a meeting with you individually to resolve your doubts. Your end of module assessment, or the EA, accounts for the remaining 40% of the grade. The EA will be a quiz, also through Moodle. It will comprise of 50 questions and you will have 1 hour to finish it. We will announce the schedule of your EA at a later date because this will need to happen in person at one of our labs at HKDI. The good thing about the EA is that it shadows the CA in almost every aspect. The types of questions are the same, all multiple choice and true and false type, and quite a lot of it are actually from the CA itself. Which means, if you do all of the CAs on time, practice the exercises in the book and revise properly, it is very easy to get a high score even in this. In fact, if you score over 70% in the EA, you are eligible to appear for the official Pro Tools 101 exam. It's an exam that usually costs over $5,000 to give, but you're getting an opportunity to do it for free, so don't waste it. Once you clear the Pro Tools 101 official exam, you are eligible to enroll for the Pro Tools 110 course as well, which we usually run in the summers. As I had mentioned in my introductory video, the textbook also comprises of 2 hands-on exercises. One of them is for practicing tasks involved in music production, while the other makes you practice tasks involved in post-production. These hands-on projects are not graded, so you don't have to submit them to me. They are for you to practice at home on your own time. So while we will not go over them in this class, if you do come across a doubt or a problem when you are practicing, feel free to reach out to me. I'd be glad to help you out. I'd like to start today by talking a bit about the fundamentals of sound. These are concepts that you have studied previously in Acoustic and Sound Basics in Semester 1, but I think it'll be good for us to revise them. If we are asked what is sound, how would we go about defining it? We all know what it is, but sometimes it's not easy to put into words something that seems so obvious. Many times words associated with sound come to our mind when we are asked to define it. Words like waveform or frequency or vibrations. But when we string these words together, we can actually get a definition. Sound is defined as vibrations that travel through the air or another medium that can be heard when they reach a person's or an animal's ear. It's quite simple actually. We need a source for the sound and a medium to carry the sound from the source to us. But of course, the sound itself needs to be within a frequency range and at a volume level that we can hear. Putting this definition of sound into a visual perspective, let's say I have this speaker. We all know how a speaker works. When the signal is fed into it, the cone comes out and in with respect to the shape of the signal. So how does the sound come to us or our ears from the speaker? Sound always needs a medium, a carrier. If there's no medium, there can still be sound, but we won't hear it. The medium can be a solid, a liquid, or simply air. An example of a solid medium would be the walls of your room. If you are in a closed room, you can still hear sounds from outside the room. That is because sound can travel through solids. Similarly, an example of a liquid would be water. When you go swimming, if you try to, you can hear sounds coming from outside the pool even when you are underwater. Of course, in both these cases, the sound isn't pure. Frequencies do get filtered, and the speed at which the sound travels through these mediums is different. But when the medium is air, how exactly is the sound coming to us from the source? It reaches us through the modulation of the air pressure. Let's take a look at the speaker again. When we play a sound through the speaker cone begins to move. Every time it comes outward, it pushes the air particles that are right outside, thereby increasing the air pressure. When it goes inward, it sucks the air particles, thereby reducing the air pressure. If you're wondering how that works, think of a time when you went to the beach. I'm hoping you'll have all been to the beach at some time in your lives. When you're standing right at the edge of the water and waiting for the water to come and touch your leg, think about the sand that is right under your leg at that moment. When the water comes and touches your feet, all the sand comes together. It becomes firm and you're able to stand tall. That is because the water increases the pressure in the sand. But as soon as the water begins to recede and go back, you will feel your balance giving way. You will feel like your feet are now sinking into the sand. That is because the sand is getting pulled back into the sea by the water, and the pressure that was holding it firmly till now has begun to reduce. This is exactly how the speaker changes air pressure too. When it comes out, the air pressure increases. When it goes back in, it sucks the air, thereby reducing the pressure in it. Let's map this change in air using a simple XY graph of pressure along the y-axis and time along the x. So when the speaker cone comes out, it increases the pressure in the air. When it goes back in, it reduces the pressure in the air, and then it reaches its original starting point. This is why when we see sound, we see a waveform, because it's actually just a graph that shows us the changes in air pressure. The region of the waveform that is created when the pressure in the air increases is known as compression, and the region of the waveform that is created when the pressure decreases is known as expansion. Whenever a waveform completes a set of compression and expansion, it's called a cycle, and that is what determines our frequency. The number of cycles that we have in 1 second is what is defined as frequency. The size of the waveform when you measure it vertically is its amplitude, or more commonly known as the volume. So these are the three properties which will define every piece of music that you make. Waveforms, which are variations in sound pressure that reach our ears when created by a sound source within a frequency range that we can hear. Frequency is basically the number of cycles that are made per second. It's measured using the unit Hertz. And amplitude, which is the strength or the intensity of the waveform when it reaches our ears, creating the perception of loudness. Amplitude or sound levels are measured in decibels, dB. As future audio engineers, it's important to remember though that decibels is not a normal mathematical quantifier, which means we can't add and subtract dBs like we do normal math. As you learned last semester, a dB is a logarithmic scale, so just doubling the number does not necessarily make it double. When it comes to amplitude or volume, you need to always remember two values, 6 dB and 20 dB. 6 dB is how much you need to add to your signal if you want to double its amplitude, and 20 dB is how much you need to add to your signal if you want to multiply its amplitude 10 times. If you wish for the reverse, which means if you want to make the volume half, you need to reduce the amplitude by 6 dB. And if you want to make the volume 1/10, you should reduce it by 20 dB. So when you get into mixing and the level of a track is 3 dB, making it 6 dB is not actually double the volume. If you want to make it double, you have to add 6 dB to the current value, which means 3 dB should become 9 dB for it to technically be double the volume. Let's now talk about how we take this waveform and get it into our digital audio workstation. A sound waveform is analog, but computers are digital. Computers can't understand waveforms. In fact, they can only understand one language, and that is the language of ones and zeros called binary. Whatever we wish the computer to understand must be translated to binary. The process of converting our analog waveform into binary information is called analog to digital conversion, or ADC. There are two elements that are used during this conversion process. One is the sample rate, and the second is bit depth. Let me explain what bit depth is first. A bit is basically a binary digit, which means it can be a 1 or a 0. Bit depth is how we define how many bits we use when we convert our waveform from analog to digital. So if we are to use a 1-bit system, we can have only 2 unique values, 0 and 1. If we are to use a 2-bit system, we can have 4 unique values, 00, 01, 10, 11. Similarly, if we use a 3-bit system, we can have 8 unique values, 000, 001, 010, 011, 100, 101, 110, and 111. We can actually calculate the number of unique values by raising the number of bits to the power of 2. So, a 3-bit system gives us 2 raised to 3, which is 8 unique values. A 4-bit system will give us 2 raised to 4, which is 16 unique values. The more number of bits we use to record, the more unique values that we can use in our conversion. Similarly, a 5-bit system gives us 32 unique values. And as we go on, a 16-bit system will give us 2 raised to 16, which is 65,536 unique values. So how does this number matter? Why do I need so many unique values? What are these unique values? It matters because these unique values are actually my volume levels of the converted signals. Let me put this into a visual for you. Say this is my analog waveform. For me to be able to translate this or convert it to binary, I would need to somehow tell the computer what this waveform looks like. We need to measure this. and this measurement is done using sample rate and bit depth. The waveform is first sampled at a regular interval, which means we identify points along the waveform at fixed intervals so that the computer knows where the waveform is actually positioned. Once the samples are defined, we assign each of them a binary value, because that is the only thing the computer can understand. So if we use a 4-bit recording system, it means we have 2 raised to 4, which is 16 different values, starting from 0000 all the way up to 1111 that can be assigned to our samples. If we look closely, many of these dots do not correspond exactly to our bits, which means the samples will be assigned the binary number that is closest to it, and that is what the computer gets. The computer will redraw the waveform in our digital audio workstation based on these samples. And if you look closely, because of the lack of proper information, the waveform that it recreates is quite different from what we actually had. This is our original waveform, and this is what the computer has recorded. We can see how different both of these are. Thankfully, it isn't difficult to fix. To ensure that the waveform the computer generates is as close as possible to our original analog waveform, all we need to do is ensure that we have more number of samples. But just having more samples isn't enough, because if we do not have enough binary values to assign to those samples, we will still get a bad waveform. So we increase the bit depth as well. Using a 16-bit recording system, for example, will give us 65,536 unique binary values to assign to our samples, which is great because these binary values are actually the volume or the amplitude information about each of the samples in our waveform. So the more we have, the more accurate the position of our sample will be within our system. Now imagine using a 24-bit system to record. A 24-bit system gives us 2 raised to 24, which is nearly 17 million unique values that we can assign to our samples. This means we can achieve an even more accurate recording using 24-bit bit depth. This process of sampling our waveform and assigning every sample with the binary number is what we call ADC, or analog to digital conversion. This is the job of your audio interface. Good interfaces do this really well, which means the accuracy of the waveform recorded in your digital audio workstation is much higher. That is why some interfaces can be expensive, because their conversion quality is very good. There are various sample rates that can be used in the recording process, starting from 44,100 all the way up to 192,000. Some of the interfaces can go even higher now, like 384,000 and 768,000 as well. But not all DAWs can work with that many samples. Like Pro Tools maxes out at 192,000 or 192K. You can even choose your bit depth when you're recording. You can record in 16-bit, 24-bit, or even 32-bit floating point. A higher bit depth gives us much more detail in our recorded waveform in the form of a higher dynamic range. If you all recall from your module last sem, dynamic range is defined as the difference between the loudest and the softest parts of your signal. So if I'm recording an acoustic guitar, there can be a greater difference between the loudest part of my signal and the softest part of my signal, thereby giving me more detail in my recording of that instrument throughout. Dynamic range can be determined from our bit depth itself. Every bit that we use gives us 6 dB of dynamic range, which means if we are recording in 16-bit, our recorded signal will have a dynamic range of 16 into 6, that is 96 dB of dynamic range. If we record in 24-bit, our recorded signal will have a dynamic range of 24 into 6, that is 144 dB of dynamic range. Recording in 32-bit is a bit different though, it's not a straightforward math. So we'll cover that in our recording and mixing module. Many of you may be wondering why the sample rates that we use in the recordings are such an odd number though, like 44,100 samples per second or 88,200 samples per second. What is the rationale behind using such a number? Why not just use a nice rounded 50,000 or 100,000 samples per second instead? These numbers may seem random, but they actually have to do with our, that is, the human, hearing range. I'm sure you know, our hearing range spans from 20 Hz to 20,000 Hz or 20 kHz. So when something makes a sound, like let's say a dog is barking, do we know exactly what all frequencies there are in the sound that the dog is making? Not necessarily. We know the dog is making a sound because some of that sound is in a frequency range that we can hear, which is 20 to 20K. But that does not mean there are no sounds in any other frequencies. I'm not saying there absolutely is, I'm just saying there could be. For our computer to be able to recreate the waveform we are listening accurately, Nyquist and Shannon, two scientists, did research and figured that if a signal is sampled at double the maximum audible frequency, it can be recreated accurately digitally. Which means, if I wanted to ensure that everything up to 20,000 Hz was recreated accurately in the computer, we should sample our signal at double that number, which is 40,000 samples per second. If I wanted to ensure that everything up to 40,000 Hz was recreated accurately in the computer, we should sample our signal at double that, which is 80,000 samples per second. While our listening range is defined, we need to define the listening range within a computer as well, because otherwise, our computer would waste precious bits into sampling sounds that we can't hear. So, the signal that gets fed into our interface should only be in the frequency range that we can actually hear. And the way we do that is by filtering out the frequencies that we can't hear. Unfortunately though, a filter can't be applied as a sharp cut. It always has a slope. So if I applied my filter in such a way that it ends at 20,000 Hz, I actually lose out on some of the sounds or harmonics which I need. So to ensure that everything I need is included, I extend this filter to start after 20,000 Hz, which makes us include audible frequencies until 22,050 Hz. So if we have to sample this signal so that it is accurately recreated in the computer, I have to sample it with the number of samples that is double this. So double of 22,050 gives us 44,100. This is how we get the 44,100 as a sampling rate. The maximum audible frequency of our recorded signal is dependent on the sampling frequency. Recording at higher sampling rates will ensure that our computer can accurately recreate the waveform at higher frequencies. This maximum audible frequency is also called the Nyquist frequency. It's easy to calculate, just half the sampling rate that you're recording in and you get the Nyquist frequency. So this is how we get our signal in to our system. The reverse process is called digital to analog conversion or DAC. Again, this too is the job of our interface. It takes the samples along with the bit information from our digital audio workstation and creates the waveform and then feeds that to our speakers. But what if you're recording a signal that needs no conversion? Like, for example, if you're recording something that is already digital, should we still do a conversion? It's important to understand that in the world of recording, every conversion you do will reduce the quality of the original signal. So if you need something in the digital realm that is already digital, we should not convert it. For example, music that's on a CD. A CD is digital. The signal in it is stored at a sample rate of 44.1 kHz and 16-bit. So if I wish to bring in this signal into my digital audio workstation, I can do so without any conversion. because both my source and my destination are already digital. There are two connection types that I can use to transfer audio digitally into my digital audio workstation from an external source. The first is what we use mostly in the professional or studio environment, called AES-EBU, or the Audio Engineering Society European Broadcasting Union format. The connector for this standard is actually an XLR, so it looks exactly like a microphone cable, but the signal that is transferred on it is digital, not analog. The second is a more consumer standard, and while it is still used in studios, it isn't as preferred as the AES connection. SPDIF, or Sony Philips Digital Interface, uses the RCA connectors to transfer signals from one digital device to another. It is quite commonly used with home theater equipment too. So now that we know that recording at higher sample rates and higher bit depths will always give us great signals, why don't we record at the highest possible numbers? The holdup here is actually storage. When we record at higher sample rates and higher bit depths, our converted audio signal takes up more space on our hard drives as well. As future recording engineers, it's always good to know whether you have enough hard disk space to do your recordings before you start your recording. You do not want to be in a situation where your hard disk becomes full right in the middle of recording a band. Calculating your storage needs is very easy. Let's say I want to record 1 minute of audio at 48K and 16-bit. So, 48,000 samples times 16 bits gives me 768,000 bits for every second of audio. Since 8 bits make 1 byte, 768,000 bits is 96,000 bytes. To convert from bytes to kilobytes, I divide by 1024, as we have 1024 bytes in every kilobyte. So that gives me 93.57 kilobytes. To convert this to megabytes, I divide by 1024 again, as 1024 kilobytes is 1 megabyte. So this gives me 0.09 megabytes, and this is still for 1 second of audio. Since I want to know how much space I need for 1 minute, I multiply this answer by 60, as we have 60 seconds in 1 minute, and that gives me 5.49 megabytes per minute. Now, while this math isn't difficult, it is quite a few steps, so thankfully I have found us a shortcut. Whenever you need to do math like this, the first thing you need to do is take the sample rate and bit depth and multiply them. And whatever answer you get, just divide that by this number, 139810. This will give you the amount of hard drive space you need for 1 minute of audio in megabytes. Let's take the same example again. 48,000 samples and 16 bits. So 48,000 multiplied by 16 gives us 768,000 bits per second. I divide 768,000 by 139810 and I get 5.49, and this will be megabytes per minute. Give it a try. With any sample rate and bit depth, you can't go wrong. The magic number you need to remember here is 139810. So this brings us to the end of this part from Chapter 1. We have covered the basic principles of sound and the core fundamentals of recording. All of this is really important for you to be able to understand the functioning of a digital audio workstation like Pro Tools. I hope my teaching pace is okay for you to understand and follow along. Please reach out to me if there's anything that you have not understood or would like for me to explain again. We can use our channel in Teams to discuss any point that you all wish, so feel free to start a post that everyone can contribute to and benefit from. This lecture will also be made available to you to watch again over Moodle, so feel free to log in and watch it at your own pace. So until we meet next time, take care, stay safe, and stay healthy. Bye-bye.